Jai Hind. The topic which we are going to discuss today is MapReduce related to Hadoop. We have already seen what is Hadoop, what is HDFS, how HDFS interact with Yarn. We have seen a simple introduction of MapReduce there also. Now we are starting basically what MapReduce is. So when we say a MapReduce, it is a framework which we use for writing the applications to process huge amounts of data, that is basically for analyzing the data, big data. And when you are analyzing the big data, you are doing this operation in parallel. And on a large clusters where this data is basically stored, and where these large clusters, they are comprised of commodity hardware. So MapReduce, it is a processing technique and a program model for distributed computing based on Java. As we have already seen when we have discussed the Hadoop concept, we have seen that it is meant for the distributed system. It utilizes the concept of distributed system, and there we are having the file system which is known by the name HDFS. So basically MapReduce, it interacts with this data cluster on which we are having HDFS. Abstract issues of distributed and parallel environment from programmer. Since we are aware in the Hadoop, we have seen that we are having the computing clusters available with us, and data is being distributed all over these nodes. We are running the computation on each and every node. That is, we are doing the computation in a distributed environment. So in that case, if the user is aware that he is working on the distributed environment, then for him it becomes very tough, very difficult how to design the applications in such cases. So Hadoop, it provides an MapReduce, it provides an environment where the programmer does not need to worry about that its application is running on the data. It is using the data which is distributed throughout the clusters. Moreover, the programmer does not need to worry about the parallel environment, because in the MapReduce concept, what we will do, we will reduce the data and we run the application parallel on different nodes. We will see later on how we achieve this concept with the help of MapReduce. So basically it runs over the distributed file system. In the Hadoop, we have seen HDFS, and we are having other file systems available, distributed file system available with us, for example Google file system. So MapReduce algorithm, it comprised of two important tasks. One is map and another one is reduce, and that is why the name come MapReduce. If we want to do the data processing in the classical or the traditional environment, or you could say in a non-distributed environment, then what will happen? Here we are having CPU, memory and the disk. We want to, when we run a program, these are the hardware which we generally use. So in that case, in a single node machine, data fits into the memory, that is from here the data comes here. In CPU, what will happen? The instructions, it will start executing. So we load the data from disk into memory and then process from memory. If the data does not fit into the memory, then we use the concept of virtual memory. That is, we will load the part of the data from disk into the memory and then process the data. What is the why we can't use the this concept, that is classical data processing, and why we are going towards the MapReduce? For example, we are having 10 billion web pages, and per average size of web page is approximately 20 KB. Then how much total size become? It will become 200 TB. For example, for disk read bandwidth is 50 MB per second. Then to read this much data, is approximately 4 million second, and if you convert it into days, it will comes approximately 46 days. And if our data increased, then just we are performing only the simple read operations. That's it. We are doing nothing in this case, and still the time for 200 TB, it comes out to be 46 plus days. Now what will happen if the size increase? So if we want to use traditional systems, then they are not useful for the data analytics. So what is the solution? The solution is use multiple interconnected machines. For example, we are having the big data. We will split this data into small chunks, and we will distribute this data to different nodes. These send to different machines, and we do the processing on these machines in parallel. Once the data come, we will collect the results from different machines and then produce the aggregated output to the user. So basically, if we look at this architecture, it comprised of distributed data processing. This is a concept of distributed data processing which we use in clustering. So now comes why we go for the MapReduce. As in the previous example, we have seen that we require the large concurrent systems. Grid computing concept may be used, or we can go with other solutions which we have designed. But what is the limitation with all these existing solutions? Threading is very complex. That is how you distribute that thread in the parallel environment. How do you scale to more machines? Once your data increased, you need to bring more machines into the system. How do you handle the machine failures? If one of the node failed, then what is the impact, overall impact on the system? How do you facilitate communication between the nodes? If two nodes want to interact with each other, how you will handle that communication? Does your solution is scalable? So these are the various questions, or you could say challenges, and which are coming if we are using the concept before the MapReduce. So how MapReduce addresses the challenges? Data loss prevention, that is by keeping the multiple copies of data in different machines. So if machine fails, we have the copy of our data present on another machine. Data movement is minimization, that is a communication part. Now what we are doing, instead of moving the data, what we are doing, we are moving the computation. That is, send your computer program to machines where the data is residing, and there we are doing the processing. And complexity, how we have reduced the complexity of the previous systems. We are doing two operations in this case. One is map and another one is reduce. So the programmer will write only these map and reduce programs or functions. He need not to worry about it, how to, what is a distributed, what kind of distributed architecture is lying within, how you need to aggregate the solutions, how the parallel, if the instructions they are executing parallelly, how the things would be solved. Or the programmer, this is not the headache of the programmer if he is using the MapReduce concept. So as a programmer, you do not need to worry about other things. You just focus on writing how to write map function and how to write the reduce function. So what is the basic concept of MapReduce? All the data is represented in key value pairs of an arbitrary type. With the help of example, we will see what it implies. Data is read in from a file or the list of files, and maybe these files, they are residing on the distributed file system, for example HDFS. Data is chunked based on an input split. For example, a typical chunk is 64 MB, more or less can be configured depending on our use case. That is, we are dividing the data and we are distributing this data on different nodes. And we are also keeping the copy of this data on other nodes. So mapper, we are having map and reduce. Corresponding to map function, we are having mappers. The mappers read in a chunk of a data. Mappers emit. There is a function emit. What it implies? Write out a set of data typically derived from its input. That is, it will read something and it will produce a output, and this process of producing the output, it is emitting the data. Meanwhile, some intermediary data is also produced, and this intermediary data is split to a number of reducers. Intermediate data which we are getting from the mappers. We are calling this intermediary data, and we are splitting it to a number of reducers. Now, what the reducer, that is reduce function, will do? It will receive each key of data. From each node, it is getting key value pair along with all of the values associated with it. This means each key must always be sent to the same reducer, and this is the key. Then we are having set and the value of set. The reducers, they will generate output. Again, it is emit a set of data typically reduced from its input, which is written to the disk. So basically what is happening, we are having the input, we are splitting this input and storing them on different nodes in a cluster. Then on every split, a mapper is working. It is producing some intermediary result, and this intermediary result is sent to a reducer. Maybe these reducers, the data from this mapper is going to both of the reducer, and same thing happened with mapper 1 and mapper 2. These reducers, they are generating, they are performing some action on this intermediary result, and from there each reducer is generating their own output. So map function, it takes a set of data and convert into another set of data where individual elements are broken down into tuples. That is, we are having a data and we are breaking down this data into key value pairs. Secondly, then the reduce task come into picture, which takes the output from a mapper as an input and combine those data tuples into a smaller set of tuples. As the sequence of the name MapReduce implies, the reduce task is always performed after the map job. That is, this data flow is always maintained. First we do the mapping and then we do the reduction. The major advantage of MapReduce is that it is easy to scale the data processing over multiple computing nodes, since we are distributing the data on different nodes. Under this model, the data processing primitives, as we have seen, one is mapper and another one is reducer. Decomposing a data processing application into mappers and reducers is sometimes non-trivial, but once we write an application in the MapReduce form, scaling the application to run over hundreds or thousands or tens of thousands of machines in a cluster is merely a configuration change. That is, once we write a mapper function and the reducer function and our data got scaled up, then we don't need to change the code. We don't need to change these functions. What we will do, we will just change the configuration part, and the mapper and the reducer function itself will handle all the things. And due to this concept, we will achieve the concept of scalability. That is, we are not concerned how much data we want to process. So, MapReduce algorithm, basically it will execute in 3 stages. One is map stage, then comes the shuffle stage, and then comes the reduce stage. What is map stage? The map or mapper job is to process the input data. Generally, the input data is in the form of a file or directory and is stored in some distributed file system, for example HDFS here. The input file is passed to the mapper function line by line. That is, the mapper function read the lines of your file. Then the mapper process this data and create several small chunks of data. Now the reduce state, this stage is the combination of the shuffle stage and the reduce stage. That is, we perform both the actions here. The reducer job is to process the data that comes from the mapper. After processing, it produces a new set of output which will be stored in the HDFS. So we are having input data, passing it to the map. Map is doing some function, then we are passing this to reduce function. After that, this reduce function is sending the data to some other machine where we are joining the output and then storing this joined output data in the HDFS. We have already seen the HDFS architecture in Hadoop. This is just for a revision kind of thing. So in the HDFS architecture, what we have seen, this is my master and here I am having slaves. In the master, we are having name nodes and the secondary name nodes, whereas in the slaves machines, what we are having the data nodes. We are calling them as data nodes. On the data nodes, we are storing only the data, whereas in the case of the name node, we are keeping the information of our file or the data which we have stored on these data nodes. That is, we are keeping the meta information of all this data in the name node, and the secondary name node, it is acting as a backup. So for example, at the client side, we want to perform some action on a file now, or we want to read a file. Then in that case, we will send the file name. This file name, name node will receive it. It will search its own database. From there, it will get which block IDs it need to work on and what are the data nodes. It will send this to the client. Now the client will come to know that where exactly the data is residing, and from there the read write operation starts between the client and the data nodes. How we insert the data into HDFS? The MapReduce framework operates on key value pairs. That is, framework views the input to the job as a set of key value. The key and value classes should be in serialized manner by the framework and hence need to be implement the writable interface. Additionally, the key classes have to implement the writable comparable interface. So the input and output types of MapReduce, the input is K1, V1 map, and reduce we are getting the K3, V3 as an output. So the different terminologies which we use here: payload, applications. These are the applications which implement the map and reduce functions and form the core of the job. We are calling them as payload. Then the mapper, we have seen it maps the input pairs to a set of intermediate values. Name nodes, that manages the HDFS. Data nodes, where the data is kept. Master node now in the these are the nodes where job tracker runs and which accepts the job request from the clients. We have seen all these things when we have discussed the Hadoop. So slave node, where map and reduce program runs basically. Job tracker schedules the job and tracks the assigned jobs to the task tracker. Task tracker tracks the task and reports status to job tracker. Job, it is a program. Task, it is the execution of a mapper or a reducer on a slice of data. And the task attempt, that is the particular instance of an attempt to execute a task on a slave node. Now we will see how MapReduce works. Consider the problem. Let's consider an example where we want to count the number of occurrences of each word in a large collection of documents. So we are having, for example, so in this case, we want to count how much time this has appeared in a document, how many times is has appeared in a document, A, class, and so on. And we are aware that this is not a single file. We are having a large, huge collection of documents on which we are doing some analysis kind of thing. So how would we run it in parallel? Because since we are having, for example, 10 files, and if we run the code on these 10 files sequentially, then it will take a lot of time. No doubt we want to go with the parallel concept. So the solution may be divide the documents among the workers, that is your slaves in this case. Each worker, that is a slave, it passes the document to find all words outputs, and this words and output it will form, it is key, and this is value, that is count. Then we partition the pairs across the workers based on word. For each word at a worker, we locally add up the counts. So here, file too large for memory maybe, but all word count pair fits in the memory. It might be a case 1. So you can create a big string array, or you can create a hash table in this case, how you will store the word count pairs. In another case, all these pairs do not fit in the memory but fit into the disk. So a possible approach, write computer programs or functions for each step. So what are the steps? Break the text document into sequence of words, then sort the words. This will bring some words together. Then count the frequency in a single pass. That is, break the text document, get the words, then we sort, and then we go with the counting part. So the case 2, it is very near to about the MapReduce. So MapReduce, first get words from the data file. This becomes the input. Then we sort it, and after sorting we count it. So in the map, what we are doing, extract something you care about. That is here word and count. Then group by key, that is sorting and shuffling. That is here, for example, we got the, it repeats 2 times. Then we are having is, maybe it receives 3 times. Maybe after it, we are having A, it is repeat 10 times. So here we will do the sorting and shuffling on the key value. After that, we will reduce it, aggregate, summarize, and save the result. That is in the counting part. So what's the summary? Outline stays the same as we have seen earlier, but map and reduce to be defined to fit the problem. So programmer's responsibility here becomes just to design map and reduce function. So we will input the key value pairs, file name and its content in this case. That is file name, and these are the contents of this. Now what we will do, we will pass it to different nodes. On these are the nodes. Here we are having file names and the content. Then we give it to the mapper function. The mapper function, it will produce the intermediate results, and these results, what they are comprised of, here the key value, it becomes word and count. So these are the keys and these are my count. Now we group by. The reduce step, what it will do, we have got the intermediate results, we pass it to the reduce step, it will group this by the key values. If you look here, then what is happening, each mapper function is giving its own set. Now what the reduce function do, it will group all these things. So here corresponding to key K1, we are having values V1, V3, V6 and so on. We reduce this and we get the final output. For example, here we are having the big document. This is the document. Here the key value, that is provided by the map function. Here we have read the input and produces a set of key value pairs. What is happening in this document, the is appearing 1, crew and so on. So here group by key, that is collect all the pairs with the same key. So we have seen this. This is all the pairs with the same key. So if we say, then it will becomes crew 2 and so on. It will become the 3 because it has appeared its count is 1. So here the at the your reducer level, what will happen? It collect all the values belonging to the key and output the result. So here we are having the final thing which we want to do. This we want to perform. So this is how the things are being taken with the help of MapReduce function. We are reducing the things. So what is the pseudocode? The user need to write only the map and the reduce function. So here for each word W in value, it is emitting, that is outputting W and 1. Similarly, here the value result we are counting. So initially it is 0 for each count V in values. Here we are again the output is coming key and result. So user need to worry about the code only of the map and the reduce. Since we are running the MapReduce, this we have seen in a single machine. But since we are aware that the MapReduce, it is working in a distributed environment. So in this case, what is happening? These are the nodes. So we are having map task 1 on one machine, map task 2 on another machine, map task 3 on another machine. Each is producing some result, and then they are sending what they are getting, they are sending to each and every machine. And reducer, these reducers, they are sorting the things and finally producing the output. Now the question comes, since MapReduce, it works on a distributed environment and it uses the concept of parallelism. So we need to identify what kind of applications we can design with the help of the MapReduce. Not all applications they are suitable for the MapReduce. So the problems which are suitable for MapReduce, it is suitable basically for batch processing because we can break down the things into parallel. We can utilize the concept of parallelism over here. So updates are made after whole batch of data is processed. The mappers do not need the data from one another while they are running. For example, we have seen the word count. In general, MapReduce is suitable if the problems, they can be broken down into independent sub-problems, and the output of one problem is not to be sub-problem is not acting as an input to another sub-problem. They are totally independent. So there we can use the MapReduce framework easily. But the problem comes when the machine needs to exchange data too often during computation. Then we don't go with the MapReduce concept. For example, an application that require very quick response time. So for example, in IR systems, indexing is okay, but query processing is not suitable for MapReduce function. Machine learning algorithms, they require frequent parameter updates. So for example, stochastic gradient descent. So again, such applications which we are building over the ML concept, we generally don't go with the MapReduce concept. So MapReduce, it provides a simple way to scale up your application. It scales out to more machine rather than scale up. Effortlessly scale from a single machine to thousands, fault tolerant and high performance, as we have seen. If you can fit your use case to its paradigm, scaling is handled by the framework. You just need to think about, can your application go with the MapReduce framework? If the answer is yes, then go with it. The scaling part is handled by the framework itself. These are the references which I have used for preparing the slides. Thank you and Jai Hind.